Otherwise, I'll meander through the crowd while I talk. All right. They say before you start, take a deep breath. Imagine that your audience is naked. And then go. All right. So I was asked to fill in a slot in one of the concurrent sessions, and then found myself at 8 in the morning, slotted for 45 minutes. So lucky you get about 45 minutes of me talking on a subject that's particularly unpleasant for most of us to think about. But I did want to touch on the theme of sustainable water footprint in the talk. I don't want this talk to in any way distract from the very real and larger pressing issues related to water quality, access to water, water use that have been discussed already and that we still need further discussion on. But I did want to present to you a snapshot of some of the issues that are starting to emerge with respect to water. Our practices in terms of how we use water to some extent, but also how we consume water in our daily lives, either in agriculture as we practice it or as individuals as we live. So, top title that was presented is Emerging Water Quality Management Concerns in Agro-Ecosystems and Beyond. And I can't tell you how much I've been mocked about the and beyond part, but there is an and beyond part. Just as a quick introduction, I'm an agrologist associated with the Nova Scotia Institute of Agrology, and I've been a member there since I joined the NCC in 2007. So let's see if I can get this to go. Nope, okay. So we all have an intimate relationship with water. We interact with water every single day of our lives, and it sustains us. It's integral to who we are as human beings, as organisms. I remember I had the luxury as a child of growing up in Costa Rica for a number of years. My father was also an agricultural scientist, and I remember running around barefoot in the fields, going through forests, and we'd sort of follow a stream up and we'd find these little pools. We never questioned. It brought us immense joy to get into these waters, swim, play, and we never questioned that water. We never questioned the quality of the water. We just enjoyed it. And it brings us joy in our everyday lives as we recreate in it, as we bathe in the hot, humid weather. It also brings us joy as we stand back and we look out and just take a moment to be as human beings with these spectacular type of landscapes. It also brings us loss and damage and concerns, and that's a growing issue in our day today, and will continue. And it starts with food. It starts with how we produce our food, and it starts with water that's contained in our food and the other things that are associated with that water that's in our food. And so that's the nice stuff. So now it starts to get ugly. So then what happens? Well, so now we have the Goldilocks' advice on conserving water. We have the Papa Bear, the Mama Bear, and the Baby Bear. And this relates to how we consume our water, what we use it for, and what happens to that water. And the decisions that have been made historically as to why we use water for different purposes. We use it in agriculture for producing food. We use it in these modern systems in order to move things that are the food that's processed in our bodies away somewhere else. And we've learned that we can reduce the amount of water that we consume through this process. If you have an agricultural bent, you might choose to decorate your toilet in such a manner. But what do we actually contribute? I don't think we ever want to think about this in terms of pure numbers, but you need to think about it. because this is our natural function. It's a part of who we are as human beings. And we do it, we manage, if you manage livestock, you take it for granted that they're going to produce manure. And you think about how much manure they're producing because you have to manage it on a day-to-day basis, on a year-to-year basis. But with our own, we don't think about it because we pay taxes, someone else deals with it for us. So on average, each one of us produces anywhere between 80 grams to 350 grams of solids per day. So 80 grams, just so that you can picture it in your minds, I know you don't want to, is about the equivalent, 80 grams is about the equivalent of 2 chocolate bars. There's the image for it. 350 grams is about three-quarters a bar of butter. Okay? We also produce on average about 1.4 liters of urine each day. So what does that translate into something that you can imagine visually? Are you ready? So imagine that car, that's a Volkswagen, it's a modern Volkswagen deal. So about half of that vehicle, the weight of that vehicle, 600 kilograms per person per year, on average. You know, we're all slightly different, but just to get a broad perspective of how much we produce each year. That doesn't take into account the amount of water that we use to move it away, to manage it in our various systems. So hopefully, it ends up in a facility, something like this, some variation of a facility like this, where we treat it for pathogens, we treat it for that organic loading in it, we treat it for some of the nutrients, we monitor it for heavy metals and other types of general contaminants that we are aware of are concerned. Most often, it ends up like this. So the picture on the bottom right-hand side, supposedly, it's claimed to be one of the outlet pipes from the Halifax Harbor, going into the Halifax Harbor, and reportedly that is raw sewage entering into it. So you have Halifax Harbor, which has received raw and treated sewage for close to 200 years, and that's a problem. that's a significant problem. We have the technology, and this is still what we do. So what does that mean? If processed through a wastewater treatment facility, it may end up in some kind of a canal like this. It may go directly discharge into a river. It may go directly into the Bay of Fundy. And it is covered, at least in Canada and in many other countries, it's covered under a set of guidelines restricting the pathogen loads, the nutrient loads of nitrogen, phosphorus, metals, etc. So we consider this water to be clean. So the question is, are you thirsty? So as an illustration, I know it's hard to, these are all numbers, and all I'm going to do is present you with numbers and graphs from other people. I'm not going to touch on any of the research we're really doing ourselves at this point. But 4.8 billion gallons of treated effluent water enters into the Great Lakes every single day. So that's the amount of water that's consumed within, I mean, there's probably the Great Lakes Basin somewhere in the range of about 15 to 20 million people, I would say. Yeah. So it's sort of as a broad. So that's the amount of water consumed each day by that density of population. I was looking up some wastewater treatment tables, and you could sort of take out a pattern of about 2,000 liters per person per day is what's used or what's processed through most of the typical wastewater treatment. So it's not so much what we use, but what it takes in the processing of it. So 2,000 liters per person per day of water used in these systems. So what's this emerging challenge in water quality? Well, the emerging relates to the things that we consume every day, or the components of the things that we consume every day. So only half of the drugs, here's some headlines, and half of the drugs, other newly emerging contaminants are removed from the sewage system, from the wastewater treatment system. So these are your pharmaceuticals. These are the ingredients in your shampoos, your antimicrobials, in your soaps, the nanoparticles that are in your clothes or in your detergents. the EPA has a workshop on approaches to screening for risk from pharmaceuticals in drinking water. So there's an awareness that when you take a medication, whether it's an over-the-counter medication or it's a medication that's prescribed to you, and I'm not by any way saying don't, but that has the potential to enter into your drinking water. When you flush that medication down the toilet, it most definitely has an opportunity to make it into your drinking water. So there's a direct connection back into what sustains us and brings us joy, to some extent, what allows us to survive in terms of our food production. Is it a real risk? Is it a real threat? So we have registered, that doesn't mean that that's all that's out there, but we have registered somewhere in the range of about 100,000 different chemicals globally. In Canada, Canada and the US is based on the registration is based on the rate of usage or rate of sales. So it's about greater than 100 kilos per year. It has to be registered. In the US, greater than 4,500 kilos per year has to be registered. So you see that pharmaceuticals and cosmetics makes up about 12,000. Pesticides are included in that. We have industrial chemicals that make up about 42,000 different chemicals. We have polymers that are used, about 40,000. Then there's a range of other byproducts. And so these are the parent ingredients. And with most of these pharmaceuticals and cosmetics, these parent ingredients are organic compounds. So these organic compounds have the capacity to degrade. And they can degrade and they can retransform into other compounds. The metabolites may be relatively benign. The metabolites may be actually much more toxic. So what's in your bottle? Well, if you ever look at the back of your shampoo bottle or any consumer product that you purchase, you're going to find a whole list of chemical compounds that make absolutely no sense. Most of these are preservatives. Some of these are plasticizer compounds that come out of this, phthalates. Bisphenol A, which has been banned from infant products, antimicrobials, absorbents, surfactants. There's all sorts of compounds that are in that mixture. Fragrances or musks. So your apple, kiwi, pear, scented, whatever. So these common products have things like phthalates, triclosan, which is antimicrobial, butylated hydroxyanisole, formaldehyde, parabens. You probably recognize some of these terms. They're found in all sorts of products, liquid soaps, nail products, cosmetics, pharmaceutical products. They are used as preservatives. The question is, what do they do to you, to some other living organism? You can take this with a little bit of a grain of salt. I took this off of an advocacy website, but it was a nice kind of clear table. But there's been demonstration of cancer effects. There's been demonstration that there are direct hormone disruption effects, reproductive disruption effects in other organisms. It doesn't necessarily mean that it's scaled up to us, but it has affected other organisms, which has some implication in terms of its ability to scale up to us in the future. Again, another list of ingredients. Acrylamides. We use polyacrylamides as products for flocculation in wastewater treatment plants. So we actually use polyacrylamides as a way to aggregate solids in wastewater treatment plants. They're very difficult. They're very long chain compounds, so they're very difficult to break down into the acrylamide form, but they do. Small quantities, but they can be out there. We have phthalates. Phthalates are in every plastic product that you purchase. Well, pretty much not every product. Most plastic products that you purchase. And they leach out of that plastic product, and then they enter into your body, and then they may have disruption of your endocrine system. So what happens? And so now I'm talking about pharmaceuticals as if it's just a function of, we go to the bathroom, we flush down the toilet, and okay, what can I do to stop that? But it's also our practices within agriculture. So we have human drugs or human pharmaceuticals on the left. And you have excretion, you have the sewage wastewater treatment plant process, and then it enters into surface water. It may enter into other groundwater, it may enter into plants or into soils. There's all other pathways that may eventually, the concern is that it could enter into your drinking water, into our drinking water. Veterinary pharmaceuticals that are used, antibiotics that are used, either as subtherapeutic levels or therapeutic levels, they're excreted, they go into the manures, they're land applied, they're managed in some way, they enter into the soil, they run off, they enter through leaching in the soil into the groundwater, potential to get into our drinking water. And then there are effects along the way. Landfills that don't have appropriate layering or lining, there may be leaching out of compounds that get into the leachate water, that mix into the wastewater treatment facilities, et cetera, et cetera. So there are lots of ways that these compounds enter into our environment. It's a big table. What it's meant to illustrate is that, am I just blowing hot air? So here we have studies that have been conducted across the globe, Asia, Australia, North America, Europe, and they all indicate the same thing. We find these pharmaceutical products and other products, but this is specifically pharmaceutical products. We find them in the effluent of out of our wastewater treatment plants. In some cases in fairly high quantities. These are all in, well, and I'll get to this, but I'll present it to you now. We are dealing with concentrations that we don't normally deal with. In agriculture, we're mostly familiar with parts per million. We deal with things in parts per million in kilograms per hectare. Big numbers. And then someone like me comes along and says, well, then you've got to think about things now in the parts per billion and the parts per trillion. And say, well, I mean, that's orders of magnitude outside of the scale that I normally deal with. You know, and we talked about 10 ppm of nitrate in your drinking water as being a concern, and then someone's coming along and saying, well, if you have 1 part per trillion of chlorhydric acid in your drinking water, maybe that's a concern. And like, well, that's apples and oranges. But that's the gap. See, that's the gap that we're living in. We can detect these compounds analytically at very low concentration, and we know that they're all there. And we know that they're in our effluent after treatment. So this is after the best possible wastewater treatment facility has managed that water. We still find it in high concentrations or higher concentrations. And then it gets into the fresh water, to the rivers and the canals, and they're being found in all of our surface waters, our lakes, our rivers, and then they're being found in our groundwater. It's about a 10-time reduction from effluent discharge to surface water. It's about a 100-time reduction in the concentration from effluent discharge into your groundwater. So we're reducing the concentration through some dilution effects, some other pathway. Doesn't mean that they're not there. So here we have red indicates the untreated wastewater, yellow is the treated wastewater, green is the surface water, and blue is the groundwater. So you can see that they don't all act the same way. So there's another challenge. That's another emerging challenge. So these are compounds that, in terms of emerging, what is meant is that we know that they're there. And they may have known that they've been there for a long time. We just don't know what the effect is. We don't know whether they have a direct impact on us or on some other organism. We don't know if they have a broader long-term effect. But there are the pieces of evidence that are suggesting that we need to be thinking about these compounds and their potential to have an effect. But you can see here, as we start to monitor some of these compounds, they react differently. In some cases, like the bisphenol A, from untreated wastewater to groundwater, you should see a reduction. Right? You should see this reduction in the concentration, and there's a lot of variability there, but for the most part we don't. But for galaxolide, which is a musk, it's a musk compound for fragrance, we do see a reduction, not after treatment, but after it makes its way into the surface water and then into the groundwater. So something's happening in the environment which is reducing the concentration of that compound. We hope it's degradation, but there's not necessarily the fullest of evidence to suggest that. So how does agriculture contribute? Because you're thinking, how does agriculture have anything to do with this other than we all perform the same basic natural functions? Well, we do, because antibiotics are used in agriculture on a relatively daily basis. In some countries, hormones are allowed to be used in livestock. We have other personal care products, soaps, detergents that are used. So not our personal care, but the personal care or hygiene of your animals. There are transformation products. All of these have been detected either in the drainage water from agricultural fields, from the runoff water from agricultural fields, the surface waters near agricultural fields. So we are a player in this game. How significant a player? I don't know. US data, and I know this is not a PI Atlantic Canada centered talk. I'm trying to provide you with big scale, I'm exaggerating, right? Because I want us to think about it, because the discussion needs to be out there. The discussion's out there already. Health Canada is thinking about banning triclosan from all products. Triclosan's in your Colgate total toothpaste. It's in your antimicrobial soaps. In some cases, people even put it in infant clothing wear as an antimicrobial product. We don't need it. Soap has done us pretty well. The basic soap has done us pretty well for a long time. This is an added value marketing piece. It's causing problems. But, so for instance, we have 2.2 billion livestock in the US in 2007, about 1.1 billion tons of manure as excreted. And that translates into, if you look at how much antibiotic usage or purchasing has occurred, you have 29 million pounds of antimicrobials sold for livestock use in 2010 in the US. That represents about 35% of the global antibiotic production. So antibiotic purchasing is about 35% going to livestock usage. Human as well as livestock excrete about 70% of the active ingredient in their feces. So a large proportion of that, of these pharmaceutical products, are not metabolized in our bodies. They're excreted directly as the parent ingredient. As I mentioned, there are, and I know this doesn't necessarily apply in Canada, but there are different rules in different places. So, and it doesn't mean that just because there are different rules in different places that these effects don't apply to us. We live in a global system where things move. So hormones that are used in the US amount to about 700,000, hormones that are excreted from livestock in the US amounts to about 700,000 pounds. Now this is in 2000 across all the major livestock groups. And then we have antibiotic resistance. You've heard of that, but here are the numbers. So antibiotic resistance. So when you have antibiotics that are being excreted in manures as the main ingredient, and then they get applied into an agricultural context or some environmental context, they have that same antimicrobial effect in that environment, whether it's water, whether it's soil. And so as we apply stress in those environments, other organisms that are able to adapt to that, adapt. And then we start to see antimicrobial resistant strains. So we can see that for E. coli, what's been found is in swine, and so these are different antimicrobials for different livestock groups. 60% are resistant to greater than 2 antimicrobials. Dairy cows, 28% resistant to 1, 6% resistant to greater than 3. Poultry, about 28% resistant to 1, 12% resistant to greater than 3, and it goes on. So we know it's out there. We know that the microorganisms are adapting to what we're putting into that environment, and they have ramifications back on us. Again, another sort of table looking at sort of the ecological risks. So most of these ecological risks are done in lab settings or in some kind of a controlled setting. But they're meant to be a warning marker. Not to say this is the real, if you are exposed to this right now, which you probably already are, then this is what's going to happen to you. They're meant to be a marker for us to be aware of into the future. So you have ibuprofen. Everyone's familiar with ibuprofen. The risk to aquatic environments is a chronic effect. So these are compounds that are entering into the system at low concentrations on a regular basis. They're entering into it every day. And so we're looking at ranges of about 0.01 micrograms per liter. So now we're starting to enter into the parts per billion range. So 0.01 parts per billion is where we're starting to see some type of reproduction impact on fish. So some Canadian work has looked at the effect of estrogenic compounds in waterways. So you can see that the ethanol estradiol EE2, which is a synthetic estrogen, birth control pills, has caused some feminization of male fish at concentrations in the range of 0.32 to 0.96 nanograms per liter. So now this is the reality of what parts per trillion means, that at concentrations less than 1 part per trillion, we're starting to see an effect on fish. Now, at 5 to 6 parts per trillion, in a study done by Karen Kidd in New Brunswick, they spiked a lake, a nice, pristine, untouched lake. They spiked it with EE2, and after monitoring for several years, they saw that the population of the fish population was altered in terms of the effect on that. The concentrations are at the bottom are the concentrations that have been found in either effluent or in surface waters in different locations. So you can see that in the U.S., they have found up to a maximum of 273 parts per trillion in stream waters. So here's a little bit from Karen's study. Really, the critical piece to see here is that the scale changes. 1, 2, 3, 2,000, 4,000, 6,000. There's a break there because this is the spiked lake. This is the unspiked lake. And so this is what they're monitoring is a concentration of this vitellogenin, which is suggestive of female characterization in male fish. So it's not insignificant, the potential effect of very small concentrations of these compounds. Again, is it a real risk? The WHO, so this is, I guess, the positive note in the talk. The WHO has done a study looking at risk factors associated with these different concentrations of the pharmaceutical products and has determined that at this time there is no significant risk to human health. So therefore, that should not distract us from the broader issues related to water quality, water management, water use that exist. So right now, there is no clear indication that we are directly at risk. But it's out there, and we know that at very low concentrations, at chronic exposures, these compounds have some effect on other living organisms. So the potential exists. And we're not reducing our consumption of these compounds. We're not advocating manufacturers change their formulations. We are still consuming these products. So they're only, and our populations, as been discussed throughout the last day, our population is growing, our consumption habits are growing, new markets are coming online, new people want to buy more stuff with these products. They want to get healthier. They want to have medication that's going to, all of this is going to have an impact, and it's going to impact agriculture. But I did want to provide you with some context around the other emerging set of chemicals, these nanoparticles. So these are particles that are at the nano scale, so that's very, 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 very small. They're used as coatings, they're used in cosmetics, they're used in medical pharmaceuticals, medical equipment, they're used in fuels, they're used as catalysts, they are going to be used in agriculture. They're going to be used as carriers in fertilizers, and they're going to be used as carriers of chemicals in pesticides and herbicides. Not yet, to any great extent, but it's coming. So agriculture is going to be, again, another player in the game with some of these compounds. So we don't know really what the true effect. We're starting to generate some evidence of what the effect is. We can see that the concentrations are in all of these products. They're in baked goods, they're in grain, they're in dairy, they're in chewing gum, they're in beverages. That's titanium concentrations. We can see that they make their way through the wastewater treatment systems. So the design of our current systems are not appropriate for either nanoparticles or the organic compounds, for the most part. They're just more designed for those things specifically. And there's evidence suggesting that because these compounds are so small, they're at the cellular level, smaller than the cellular level, they can get into organisms and start to affect things at the cellular level. So you can see a swelling that occurs at different exposures. So A is no exposure, and then as you move your way to D, there is greater exposure to this titanium oxide, and you can see that there is swelling of the cells. There's toxicity of silver nanoparticles to zebrafish. And these are compounds that are, again, they're a detergent. They help cleaning products be more efficient. Okay, so I think I'm almost done. So I wanted to get back to agriculture again, because we take water for granted, which is the quality and the quantity, but the quantity and the quality are not separated from each other. So here's an instance of irrigation canals in the state of Michoacan in Mexico, where I did a little bit of work, and you can sort of see it in the color. You can't really tangibly feel the smell that I experienced while I was there, but that's just raw sewage. That's raw sewage from the city of Morelia, which is about a city of 1 million people. And that's everything going through, basically going into the major river and then out. And then that river gets distributed into these surface irrigation canals into their major agricultural production area. And then eventually all of this gets aggregated again into a much smaller stream that enters into one of their larger lakes. So the practices that we engage in here through our regulatory frameworks, for the most part, prevent this. But we still may be buying products from there. But it doesn't prevent this. There are places where water scarcity, or the access to water, particularly for use in agriculture, enables that we want to recycle. And again, this is not a criticism of it, it's just we need to sort of monitor the broader perspective. That we have treated wastewater irrigation. There is a book, Wastewater Irrigation and Health, assessing and mitigating risk in low-income countries. So we use this as a development tool. How to recycle water into agriculture through irrigation. And it's a positive thing, but there are risks associated with that as well. Risks that are beyond the normal general risks that we think about. Metals, pathogens, nutrients. Because there are other things. The quality of what we're putting into the systems and what we're using water for hasn't changed, but what we're putting into that water system, to the sewage system, is different. It's changing every day. It's becoming more complex. And so we're producing food, horticultural crops, in some cases, with this kind of water source. And so invariably, there is a greater opportunity for things to get in. I'm not saying that it does, but the potential exists. I'm a soil biochemist by training, so I deal with water sort of as an after effect, because I know that what happens here in the soil can make its way into the water. But I just wanted to present to you, because it's early in the morning, and so we all had a cup of coffee. Caffeine is one of the products that is always found in the wastewater treatment system. And then when we start looking at soils, we find caffeine in soils as well. And here's one of the challenges with this particular area of work is that, so these are soils. This is Ed Top, Agriculture and Agri-Food Canada, and some colleagues did some work. And they were just looking to see, well, if we put some caffeine into soil, to a bunch of different soils, and we just kind of measure how much of that is getting broken down. You'd think, well, okay, different soils, but really who cares? Soils are soils; they're all going to act the same, but they don't. We see that our silt loam soil at the bottom here only metabolizes about 10% of the caffeine that's spiked into that soil. And then about 50% is degraded in the sandy loam and in the loam soil. So 50% still in that soil. We look at a soil now, but we're just changing the moisture content, which is what happens. It rains, it dries up, gets really wet, gets moderately wet. We've got air-dried soil, and 7% here at the bottom. And then we have the saturated soil here in the middle. And then we have the ideal moisture content that we like to have for our soils in agriculture, about 15%. And so we can see that at that ideal level, we're starting to break down more of the caffeine. And this is illustrative of any other organic compound that we put into the soil or into the system. That under the right conditions of management, the right conditions of understanding the chemicals themselves, aerobic conditions, understanding our soils, good microbial communities in those soils, we actually can manage many of these chemicals and help accelerate their biodegradation, not all of them, but many of them in the soil, under the right conditions. So we have a role to play, not just as a contributor, but as a manager. So what are the challenges? These are broad challenges. I'm not going to talk about the analytical ones, but I'm going to talk about the challenges and some of them as they relate to agriculture. So one of them is that there's just the stewardship from the science and the policy perspective. We continue to work on the detection and monitoring the environmental occurrences of these compounds. And then the next step is that we start to get a better handle on what the actual real ecological effects of these compounds are and what their potential risks to humans are. And then whether they accumulate, how they move into the system, if they move into plant material, because we consume that. And then as agricultural managers, whether you are advising agricultural managers, whether you are an agricultural manager, it's being an aware and informed consumer and a user. If you're going to buy a product to use on your agricultural land, be aware of what's going in it. Are there nanoparticles? Are you offended by that there are nanoparticles in your chemicals? Doesn't matter. And then be an advocate. Be an advocate because you're aware of the potential risk. Not because of necessarily it's an actual risk that you're going to. No one wants to necessarily harm someone directly, but you need to be an advocate and then continue the role of that environmental steward through the management practices that are going to serve well. This is the complexity of that system. This is the complexity that we deal with in our program when looking at these compounds and where they move and in agricultural systems. And you can see at the very top is the manufacturer that typically plays very little role in our lives other than producing the product. And then down here is the groundwater. And then there's everything else in between that makes its way to there. But there's value, and I found an example that I just wanted to illustrate, because now I want to go back up to the kilograms per hectare, for what we normally deal with. So we need to be thinking about these materials, not just because we need to be concerned about the negative, but also because we know that there is a positive in the materials that we discharge back into our wastewater treatment systems. That in this particular instance, this particular thesis, they were looking at the amount of imported fertilizer that's used in Uganda. So about 4,000 tons of total N, 2,200 tons of phosphorus, 1,400 of potassium. And then by looking at the amount of the nutrient concentration and the amount of material produced by the population, they estimated that the Ugandan sewage generated approximately 71,000 tons of total land, about 11,400 tons of phosphorus, and about 39,900 tons of potassium. More than enough to cover their agricultural imports of fertilizer a few times over. And we do that because agriculture sustains. So with that, I'd like to thank the group of many people that are involved in